Close your eyes for a moment and try to imagine the universe, not just the stars you can see on a clear night, not just the galaxies spinning through the darkness, but all of it, every point of light, every swirl of matter, every vast expanse of emptiness stretching in all directions. Now ask yourself a question that has haunted humanity for thousands of years. Does it end? Is there a boundary somewhere out there, an edge where space simply stops? Or does it go on forever, stretching into genuine infinity in every direction you could possibly travel? This isn't just an abstract puzzle for mathematicians to solve while sipping coffee in university offices. This is one of the most fundamental questions we can ask about reality itself. The answer shapes everything we understand about existence, about possibility, about whether the universe is fundamentally finite and comprehensible or infinite and inexhaustible. And here's the fascinating thing. Despite all our telescopes, all our satellites, all our mathematical sophistication, we still don't know for certain. Take a breath. Let yourself settle into this question. There's no rush to find an answer because the universe itself isn't rushing to reveal its secrets. We're going to explore this mystery together, moving through the ideas slowly, letting each concept unfold naturally. You don't need to understand everything perfectly. Just let the wonder of it wash over you like waves on a shore. The question of whether the universe is infinite or finite isn't just about size. It's about the fundamental nature of space itself. When cosmologists talk about the shape of the universe, they're asking about its geometry, its curvature, its topology. They're asking whether space curves back on itself like the surface of a sphere, whether it stretches out forever like an infinite plane, or whether it does something even stranger that our everyday intuition struggles to grasp. Think about this for a moment. You exist in a universe whose ultimate nature remains mysterious. You're living inside a cosmic question mark, and yet remarkably, you have the capacity to think about it, to reason about it, to use mathematics and observation to probe the very structure of reality itself. That's extraordinary when you really consider it. Throughout human history, people have looked up at the night sky and wondered about boundaries. The ancient Greeks debated whether the cosmos extended forever. Medieval thinkers wrestled with the paradox of an edge. If space ends somewhere, what lies beyond that edge? And if there's something beyond it, then it didn't really end, did it? This logical puzzle has no easy answer, and it pushed thinkers toward either accepting an infinite universe or imagining some kind of boundary that doesn't work like any boundary we know from everyday experience. Modern cosmology has given us new tools to approach this ancient question, but it hasn't necessarily made the answer simpler. If anything, our sophisticated understanding has revealed just how subtle and strange the possibilities really are. The universe might be infinite and flat, extending forever in all directions. It might be finite but curved, like the three-dimensional version of a sphere's surface, where you could theoretically travel in one direction forever and eventually return to your starting point without ever hitting a wall. Or it might have a complex topology that makes it finite even if it appears flat, folded back on itself in ways that are difficult to visualize but perfectly consistent with mathematics and physics. What makes this question so profound is that it connects to everything else we wonder about. If the universe is truly infinite, then somewhere out there, separated from us by unimaginable distances, there might be another planet exactly like Earth, another solar system. Another person exactly like you, living a life that's identical to yours in every detail. This isn't science fiction, it's a mathematical consequence of infinite space combined with a finite number of ways that matter can arrange itself. We'll explore that mind-bending idea later, but for now, just notice how the question of infinity immediately spirals into questions about identity, uniqueness, and meaning. On the other hand, if the universe is finite, that brings its own profound implications. A finite universe means everything that exists is contained within a comprehensible, though perhaps very large, volume. It means the cosmos is in principle knowable in its entirety. It means we live in something more like a bounded container, even if that container has no walls or edges in the ordinary sense. Rest now, knowing that we're going to explore all of these possibilities together. We'll travel through history and meet the thinkers who first grappled with these questions. We'll dive into Einstein's revolutionary ideas about curved space. We'll look at the observations from satellites that have measured the universe's geometry with stunning precision. We'll consider the strange possibility that space might fold back on itself in ways that make it finite even when it looks flat, and we'll confront the dizzying implications of each possibility. This is the kind of question that benefits from patience. Let yourself drift through the ideas. Let them settle in your mind without forcing understanding. The universe has been here for nearly 14 billion years. It can wait while we think about it. What we mean by shape, geometry beyond our senses. When we talk about the shape of the universe, we're not talking about shape in the way you might describe a basketball or a cube or a pyramid. Those are objects with shapes that exist in space. But the universe isn't an object in space. The universe is space. So when cosmologists ask about the universe's shape, they're asking about the geometry of space itself. This is where things start to get interesting because we need to stretch our imagination beyond the three-dimensional thinking that serves us well in everyday life. Let's start with something more familiar and work our way up. Imagine you're an ant living on the surface of a perfectly smooth sphere, like an enormous balloon. You can walk forward, backward, left, or right, but you can't fly up off the surface or burrow down into it. For you, the entire universe is just that two-dimensional surface. Now, here's the key question. Is your universe curved or flat? From your perspective as the ant, the surface looks flat. If you draw a small triangle on the sphere, it looks like a normal triangle with angles that add up to 180 degrees, just like in the geometry you learned in school. But if you draw a very large triangle, something strange happens. The angles add up to more than 180 degrees. If you walk in what feels like a straight line for long enough, you eventually come back to where you started, even though you never turned around and never hit a wall. Your universe is finite in area, but it has no edge. It's curved, but you can't see that curvature directly because you're stuck inside it. This is the situation we face with our own universe, except instead of being two-dimensional creatures on a two-dimensional surface, we're three-dimensional creatures in three-dimensional space. The space we live in might be curved in a way that we can't directly perceive because we're embedded in it. We can't step outside and look at it from a higher dimension. We have to use mathematics and careful observations to figure out what the geometry actually is. There are three basic possibilities for the curvature of space, and each one has profound implications for whether the universe is finite or infinite. First, space could be flat, which means it follows the rules of Euclidean geometry that you learned about in school. Parallel lines never meet. The angles of a triangle always add up to exactly 180 degrees. In a flat universe, space extends the same way in all directions without curving. Now, here's the subtle part. A flat universe could be infinite, stretching on forever like an endless sheet of paper. But it could also be finite if it has a complex topology that makes it loop back on itself. Imagine taking that infinite sheet of paper and somehow connecting the edges so it forms a three-dimensional version of a torus or donut shape. The surface is still flat everywhere you measure, but the space as a whole is finite. This distinction between curvature and topology is crucial, and we'll come back to it. Second, space could have positive curvature, like the surface of a sphere. In this kind of geometry, parallel lines eventually meet. If you draw a triangle, its angles add up to more than 180 degrees. A universe with positive curvature is necessarily finite, like the two-dimensional ant universe we imagined earlier. If you could travel in one direction long enough, you'd eventually return to your starting point. Having circumnavigated the entire universe, there would be no edge, no boundary, but the total volume would be finite. This is the kind of universe Einstein first proposed in 1917, and we'll explore his reasoning in detail. Third, space could have negative curvature, like the surface of a saddle. In this geometry, parallel lines diverge from each other. Triangles have angles that add up to less than 180 degrees. A negatively curved universe is infinite, extending forever in all directions. It's the opposite of the closed, finite, positively curved universe. Take a moment to breathe and let these ideas settle. We're describing the fundamental geometry of reality itself, and it's okay if it feels abstract. These concepts have challenged the brightest minds in physics, so don't worry if you need to hear them multiple times before they click. The key insight that makes all of this possible is general relativity, Einstein's revolutionary theory of gravity. Before Einstein, scientists thought of space as a fixed stage on which the drama of the universe played out. Space was just emptiness, a neutral arena where matter and energy did their thing. But Einstein showed that space itself is dynamic. Matter and energy curve space, and the curvature of space tells matter how to move. Gravity isn't a force pulling things together. It's the geometry of curved space-time. This means the geometry of the universe as a whole is determined by its contents. If there's enough matter and energy packed into space, the universe will curve back on itself and be finite. If there's too little, space will have negative curvature and extend infinitely. And if the density is exactly right, at what cosmologists call the critical density, space will be flat. But here's where it gets even more interesting. Even knowing the curvature doesn't fully tell you the shape. A flat universe could be infinite like Euclidean space, or it could be finite with a complex topology. A negatively curved universe is always infinite, but it can have different topological structures. Only the positively curved universe is necessarily both finite and simply connected. Think of it this way. Curvature is like asking whether a surface is bumpy or smooth. Topology is like asking how the surface is connected to itself. Are there holes? Does it loop back? Can you walk from any point to any other point? These are separate questions, and both matter when we're trying to understand the ultimate structure of reality. When cosmologists talk about determining the shape of the universe, they're trying to measure both curvature and topology. They want to know if space is flat, positively curved, or negatively curved. And they want to know if space is simply connected or multiply connected, finite or infinite. These are some of the most fundamental facts about reality that we can imagine discovering. Let yourself relax into these concepts. We're building the foundation for understanding what observations can tell us about the universe's geometry. In a moment, we'll travel back in time to see how ancient philosophers wrestled with these same questions, lacking our mathematical tools, but possessing the same human wonder about whether the cosmos goes on forever or curves back on itself in some mysterious way. Rest now in the knowledge that we're exploring one of the deepest mysteries accessible to human thought. Ancient philosophers and the infinity problem. Long before telescopes, before calculus, before the scientific method as we know it, human beings looked at the sky and asked fundamental questions about boundaries and infinity. These ancient thinkers didn't have particle accelerators or space telescopes, but they had something powerful: logical reasoning and the willingness to follow an argument wherever it led, even into uncomfortable territory. Aristotle, writing in the 4th century BCE, tackled the question of cosmic infinity with characteristic confidence. He argued that the universe must be finite and bounded. His reasoning went something like this: the heavens, by which he meant the sun, moon, planets, and stars, appear to rotate around the Earth once every 24 hours. If the stars extended to infinity, they would have to travel infinite distances in finite time to complete this rotation, which seemed absurd to Aristotle. Therefore, the universe of stars must be finite in extent. He also argued from the nature of place and space itself. For Aristotle, space wasn't really emptiness. It was more like a container or receptacle for material bodies. If matter itself was finite, then the space containing it should also be finite. An infinite void filled with finite matter struck him as unnatural and unnecessary. But here's where Aristotle faced a logical puzzle that has challenged thinkers ever since. If the universe has a boundary, what lies beyond that boundary? This seems like a simple question, but it opens up a deep paradox. If there's something beyond the boundary, then the universe didn't really end there, did it? The boundary wasn't really the edge of everything, but if there's absolutely nothing beyond the boundary, not even empty space, what does that mean? How can there be a place where space itself just stops? Aristotle's solution was to say that beyond the outermost sphere of the stars, there simply was no beyond. It wasn't that there was empty space out there. It's that the concept of out there became meaningless. The edge of the universe was the edge of space itself, beyond which the very notion of location ceased to exist. This is philosophically sophisticated, but it's also deeply unsatisfying to our intuitions. We instinctively feel like if we could travel to that edge and reach out our hand would go somewhere. For over 1,000 years, Aristotle's vision of a finite, bounded cosmos dominated Western thought. The universe was seen as a set of nested spheres, with Earth at the center, surrounded by the spheres carrying the moon, the sun, the planets, and finally the fixed stars. Beyond the outermost sphere was, well, opinions varied. Some said God's dwelling place. Others said simply nothing at all, but almost everyone agreed the physical universe was finite. Then came Giordano Bruno, an Italian philosopher in the late 16th century who dared to think different thoughts. Bruno proposed something radical. The universe was infinite, filled with an infinite number of stars, many of which had their own planets, some of which might be inhabited by other beings. There was no center, no boundary, no outermost sphere. Space extended forever in all directions, populated endlessly with worlds. Bruno's infinite universe was philosophically and theologically dangerous. If space went on forever, Earth lost its special place at the center of creation. If other worlds existed, humanity lost its unique status as God's primary concern. The Catholic Church found Bruno's ideas heretical on multiple grounds, and he was eventually burned at the stake in 1600. While his martyrdom had as much to do with his theological views as his cosmology, his fate shows how threatening the idea of an infinite universe was to the established order. But Bruno's vision of infinity faced a scientific problem that wouldn't be properly understood for centuries. It's a problem first clearly articulated by Johannes Kepler in 1610, though it's now known as Olbers' paradox after the astronomer who popularized it in the 19th century. Here's the puzzle. If the universe is infinite and filled with stars, then in every direction you look, your line of sight should eventually hit a star. The night sky should be completely filled with starlight, as bright as the surface of the sun, because there would be stars everywhere, at every distance, filling every possible direction. But the night sky is dark. Why? Think about it. If space goes on forever and has always existed filled with shining stars, then the darkness of night becomes deeply mysterious. Every point in the sky should glow. The cumulative light from infinite stars at infinite distances should overwhelm us, but instead, we see a dark sky punctuated by discrete points of light. For a long time, people tried to solve this paradox by saying that distant starlight was absorbed by dust or gas in space. But that doesn't really work because the dust would heat up from absorbing all that radiation and would itself start glowing. The darkness of the night sky seemed to argue against an infinite, eternal, static universe. The real solution to Olbers' paradox would have to wait for Edwin Hubble's discovery in the 1920s that the universe is expanding. If galaxies are moving away from us, their light gets redshifted to longer wavelengths and lower energies. More importantly, if the universe had a beginning a finite time ago, then light from the most distant regions simply hasn't had time to reach us yet. The night sky is dark partly because the universe is finite in age, even if it might be infinite in extent. But the ancient thinkers didn't know about expansion or the Big Bang. They wrestled with the logical puzzles of infinity using pure reason, and they discovered something important. Our intuitions about space, boundaries, and infinity can lead us into paradoxes. Common sense isn't always a reliable guide when we're thinking about the cosmos as a whole. The pre-Socratic philosopher Archytas of Tarentum, a contemporary of Plato, posed a thought experiment that captures this beautifully. Imagine you travel to the supposed edge of the universe and stick out your hand or throw a spear. What happens? If your hand goes somewhere or the spear flies off, then space continued beyond what you thought was the edge. But if something prevents your hand or spear from going farther, then there must be something there, some kind of boundary or barrier, which means there's still more universe beyond what you thought was the edge. Either way, the idea of a final boundary seems logically impossible. This thought experiment points toward the kind of universe Einstein would later describe mathematically, a finite universe with no edge. where space curves back on itself. But the ancient Greeks couldn't quite get there without the mathematics of curved space that wouldn't be developed until the 19th and 20th centuries. Let your mind rest with these ancient puzzles for a moment. These thinkers were grappling with the same fundamental mystery we're exploring, and their insights remain surprisingly relevant. They recognized that the question of cosmic boundaries isn't just about measurement. It's about the logical structure of reality itself. What's remarkable is that modern cosmology has, in a sense, returned to Aristotle's intuition that the universe could be finite without having a boundary, but instead of nested spheres with a privileged center, we now imagine curved space where every point is equivalent to every other point, where there's no center and no edge, yet the total volume is finite. The mathematics of general relativity gives us a way to make sense of what once seemed like logical contradictions. As you drift through these ideas, notice how the question of infinity has haunted human thought for millennia. It's not just a technical problem for physicists to solve. It's a fundamental question about the nature of existence itself. Are we living in a finite container or an infinite expanse? The ancient philosophers couldn't answer this question definitively, but they mapped the logical terrain beautifully, showing us the paradoxes and puzzles that any answer would have to address. Einstein's revolutionary model, a finite universe with no edge. In early 1917, just 1 year after completing his general theory of relativity, Albert Einstein did something audacious. He decided to apply his new theory of gravity to the universe as a whole. This might not sound revolutionary to us now, but at the time, it was a radical step. Most scientists thought about planetary orbits, the motion of stars, maybe even the structure of the Milky Way. But the entire universe? That seemed almost too grand, too philosophical to be the subject of rigorous mathematical physics. Einstein's relativity had revealed something profound. Space and time weren't fixed, immutable background entities. They were dynamic, malleable, shaped by the presence of matter and energy. Mass tells space how to curve, and curved space tells mass how to move. This wasn't just a new theory of gravity, it was a completely new understanding of what space and time actually are. So Einstein asked, if matter shapes space on small scales around stars and planets, what does all the matter in the universe do to space on the largest possible scale? What is the geometry of the cosmos as a whole? To make this question tractable, Einstein made some simplifying assumptions. He assumed that on the very largest scales, the universe is homogeneous and isotropic. That's a fancy way of saying that the universe looks pretty much the same in all directions and at all locations, at least if you zoom out far enough that galaxies become like individual grains in a smooth fluid. No point in space is special, no direction is privileged. The universe on the cosmic scale is uniform. This assumption, now called the cosmological principle, is both bold and reasonable. It's bold because we obviously see structure around us: planets, stars, galaxies, clusters of galaxies. But it's reasonable because when we look at the very largest scales observable, the universe does appear remarkably uniform. More importantly, the assumption makes the mathematics manageable. Without some symmetry to work with, Einstein's field equations become impossibly complex. With these assumptions, Einstein found that his equations predicted something unexpected and unwelcome. The universe couldn't be static. Space filled with matter wanted to either expand or contract. The the gravitational attraction of all that matter would cause space to collapse inward unless something counteracted it. But Einstein, like virtually every other scientist and philosopher of his time, believed the universe was static and eternal. The idea that the universe might be expanding or contracting seemed absurd. Stars were born and died, yes, but the cosmos as a whole was surely unchanging, existing in a steady state from infinite past to infinite future. To get a static solution from his equations, Einstein did something he would later regret. He added a new term to his field equations, the cosmological constant, usually represented by the Greek letter lambda. This constant represented a kind of inherent energy in space itself, a gentle, repulsive force that exactly counterbalanced the attractive force of gravity, allowing the universe to remain static. With the cosmological constant in place, Einstein found a beautiful solution. The universe could be static, finite in volume, positively curved like the three-dimensional analog of a sphere's surface, and have no boundary or edge. Space would curve back on itself. If you could somehow travel in what felt like a straight line for long enough, you would eventually return to your starting point, having circumnavigated the entire universe, just as you'd circumnavigate Earth if you walked continuously in one direction around the globe. Think about what Einstein accomplished here. He provided a mathematical model that answered the ancient philosophical puzzle: how can the universe be finite without having an edge? The answer is that space itself is curved, closed, bounded but without boundary. There's no wall to run into, no place where space stops, yet the total volume is finite and calculable based on the total mass of the universe. The geometry Einstein described is called a three-sphere, which is notoriously difficult to visualize because we're three-dimensional beings trying to imagine a three-dimensional surface curved in a fourth spatial dimension, but we can understand it by analogy. A two-sphere, the surface of a ball, is a two-dimensional surface curved in three-dimensional space. Every point on it is equivalent. There's no center on the surface itself. The center is in the higher dimension. Similarly, a three-sphere is a three-dimensional surface curved in four-dimensional space. We can't point to the center because the center isn't in our three-dimensional space. In Einstein's static universe, space had a definite radius of curvature, determined by the density of matter and the value of the cosmological constant. The universe was perfectly balanced, unchanging in time, finite but unbounded. It was elegant, it satisfied Einstein's philosophical preferences, and it solved the ancient problem of cosmic boundaries. But there was a catch. Though Einstein didn't initially realize it, his static universe was unstable. It was like balancing a pencil on its tip. In principle, if you get it exactly right, the pencil could stay balanced forever. But the slightest perturbation, the tiniest deviation from perfect balance, and it falls. Similarly, if Einstein's universe was disturbed even slightly, if the matter density increased or decreased just a bit, if the cosmological constant wasn't exactly perfectly tuned, the universe would either begin expanding or collapsing. This instability was pointed out by other physicists, but Einstein's bigger problem came from a different direction. In the early 1920s, the Russian mathematician Alexander Friedmann found that Einstein's equations, even without the cosmological constant, allowed for non-static solutions. The universe could be expanding or contracting. Friedmann showed that there were three types of possible universes: positively curved and finite, eventually collapsing; negatively curved and infinite, expanding forever, or flat and just barely expanding forever. Einstein initially dismissed Friedman's work, thinking he'd found an error, but Friedman was right, and his solutions described possible universes that evolved in time rather than remaining static. Then came the observational bombshell. In 1929, Edwin Hubble announced that distant galaxies were receding from us, with more distant galaxies moving away faster. The universe was expanding. Space itself was stretching, carrying galaxies along with it like raisins in rising bread dough. The static universe, which had seemed so natural and eternal, didn't exist. Einstein abandoned his static model and reportedly called the cosmological constant his biggest blunder. If he hadn't been so wedded to the idea of a static universe, his equations would have predicted expansion before it was observed, one of the most remarkable predictions in the history of physics. Instead, he'd added a fudge factor to force his equations to produce the answer he wanted, philosophically. But here's a fascinating twist in the story. The cosmological constant made a comeback. In the 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating. Something is pushing space apart, and that something behaves very much like Einstein's cosmological constant. We now call it dark energy, and it makes up about 68% of the total energy content of the universe. Einstein's blunder turned out to describe something real, even if he introduced it for the wrong reasons. Take a breath. Let these ideas wash over you. Einstein started with a philosophical preference for a finite, static, eternal universe. His equations told him this wasn't naturally possible, so he modified them. Observations revealed the universe wasn't static after all, but the modification he made, the cosmological constant, has returned as a crucial component of modern cosmology. Reality has a way of being more subtle and surprising than even the greatest minds anticipate. Einstein's 1917 model is no longer considered an accurate description of our universe, but it represents a crucial moment in the history of cosmology. It showed that the question of the universe's shape was something physics could address with mathematics and observation, not just philosophical speculation. It demonstrated that general relativity could be applied to the cosmos as a whole, and it provided the first scientifically rigorous model of a finite universe without boundaries. The question Einstein asked remains central. What is the geometry of space? Is the universe finite or infinite? These questions now have a framework for answering them through observation and measurement. We'll explore what those observations have revealed, but first, let yourself rest with the achievement of that early moment when Einstein showed that the ancient question about cosmic boundaries could be transformed into a precise scientific problem with, potentially, a definite answer. The expanding universe changes everything. The discovery that the universe is expanding represents one of the most profound shifts in human understanding of the cosmos. It changed everything about how we think about the shape and size of the universe, and it opened up new possibilities that even Einstein hadn't fully anticipated. Before we dive into what expansion means for the universe's geometry, we need to clear up a common misconception. When we say the universe is expanding, we don't mean that galaxies are flying outward into empty space like shrapnel from an explosion. That's not what's happening. Space itself is expanding. The distance between distant galaxies increases not because they're moving through space, but because the space between them is growing. Think of it like this. Imagine you have a partially inflated balloon with dots drawn on its surface representing galaxies. As you blow more air into the balloon, the surface expands and the dots move farther apart from each other. But from the perspective of any individual dot, it hasn't moved along the surface. The surface itself stretched, carrying the dot with it. More importantly, there's no center to this expansion on the surface. Every dot sees every other dot moving away from it. Every point on the balloon's surface is equivalent. This is how cosmic expansion works, except instead of a two-dimensional surface expanding, it's three-dimensional space itself that's stretching. And here's the crucial point. The expansion doesn't need to happen into anything. The universe isn't expanding into some pre-existing space. The expansion is an internal property of space itself. This might make your brain hurt a little, and that's perfectly normal. Our everyday experience doesn't prepare us for the idea of space itself growing. We're used to things moving through space, but we're not used to space changing its properties. Let yourself sit with the strangeness of it. Don't struggle to visualize it perfectly. Sometimes in cosmology, the mathematics works even when our intuition fails. Edwin Hubble's observations in the late 1920s revealed that distant galaxies showed a redshift in their light, meaning their light was stretched to longer, redder wavelengths, and crucially, the amount of redshift was proportional to the galaxy's distance. Galaxies twice as far away were receding twice as fast. This relationship, now called Hubble's law, was exactly what you'd expect if space itself were uniformly expanding. The expansion of the universe immediately raised new questions about its shape and size. If the universe is expanding now, it must have been smaller in the past. Run the clock backward far enough, and everything must have been much closer together, denser, hotter. This reasoning led to the Big Bang Theory, the idea that the universe began in an extremely hot, dense state roughly 14 billion years ago and has been expanding and cooling ever since. But here's where the geometry gets interesting. The expansion rate and the geometry of space are intimately connected. In the 1920s, Alexander Friedman worked out the mathematics describing how a homogeneous, isotropic universe evolves over time according to general relativity. His solutions, now called the Friedman equations, showed that three types of universes were possible depending on the density of matter and energy. If the universe has more than a certain critical density, space has positive curvature. This is the closed universe Einstein originally envisioned, except it's not static. It expands for a while, reaches a maximum size, then contracts back on itself, ending in what cosmologists call a big crunch. The geometry is like a three-sphere, finite in volume, but the volume changes over time. If the universe has less than the critical density, space has negative curvature, like a saddle shape extended into 3 dimensions. This open universe expands forever, with the expansion rate gradually slowing, but never quite stopping. The geometry is infinite in extent. If the universe has exactly the critical density, space is flat, like the Euclidean geometry you learned in school. This flat universe also expands forever, with the expansion rate approaching 0 as time goes to infinity. Whether such a universe is infinite or finite depends on its topology, which we'll explore in detail later. The critical density is a very specific number. about 5 or 6 hydrogen atoms per cubic meter averaged over the entire universe. That might sound incredibly sparse, and it is. Space is mostly empty, but the question of whether the actual density of the universe is slightly above, slightly below, or very close to this critical value determines the fundamental geometry of space. Let's pause for a moment and consider what this means. The fate of the universe, whether space curves back on itself or extends infinitely, depends on how much matter and energy it contains. The geometry of reality is determined by its contents. Matter and energy don't just exist in space, they shape space. They determine whether space is finite or infinite, whether it curves or stays flat. For decades, cosmologists tried to measure the density of the universe by counting up all the matter they could observe and calculating whether it reached the critical density. The visible matter, all the stars in all the galaxies, fell far short, but there was evidence for additional invisible matter, now called dark matter, that revealed itself through its gravitational effects on galaxies and galaxy clusters. When astronomers included dark matter, the total matter density got closer to critical, but still seemed to fall short. This suggested the universe was open, negatively curved, infinite, and destined to expand forever. But there was a theoretical problem with this conclusion. A theory called cosmic inflation proposed to explain certain features of the universe, like its remarkable homogeneity and flatness, predicted that the universe should be extremely close to flat. Any deviation from perfect flatness would have been exponentially amplified during the early expansion. So if we see the universe as close to flat today, it must be extraordinarily close to exactly flat. The tension between observation, slightly below critical density, and theoretical expectation, exactly at critical density, puzzled cosmologists for years. Then came another observational revolution in the late 1990s. Two teams of astronomers studying distant supernovae, which could be used as standardized candles to measure cosmic distances, found something shocking. The most distant supernovae were fainter than expected, which meant they were farther away than they should be if the expansion of the universe were slowing down as everyone assumed. Instead, the expansion was speeding up. The universe wasn't just expanding, it was accelerating. This acceleration required something new, a form of energy that permeates all of space, pushing it apart. Einstein's cosmological constant was back, now rebranded as dark energy. And when cosmologists calculated how much dark energy was needed to explain the observed acceleration and added it to the matter density, the total came out to almost exactly the critical density. The universe appeared to be flat after all. Take a deep breath. Let yourself absorb this remarkable story. The expansion of the universe, discovered nearly a century ago, transformed cosmology from philosophical speculation into observational science. The geometry of space turned out to be connected to its contents in precise mathematical ways, and dark energy, a component that makes up most of the universe's energy budget, was discovered through its effects on expansion. The universe revealed itself to be stranger and more subtle than anyone imagined. But expansion alone doesn't tell us whether the universe is finite or infinite. A flat, expanding universe could be infinite, extending forever in all directions, with new space being added everywhere as expansion continues. Or it could be finite, with a complex topology that makes space loop back on itself even while remaining flat. To distinguish between these possibilities, we need more than just expansion measurements. We need to probe the geometry directly. Let the question rest in your mind. In this expanding cosmos, stretching and growing, creating new space everywhere simultaneously, are we living in something infinite or something vast but ultimately bounded? The answer requires looking at the oldest light in the universe, radiation that has traveled to us from the edge of the observable cosmos, carrying information about the geometry of space encoded in its temperature fluctuations. We'll turn to that ancient light next, but for now, rest in the wonder of a universe that's not static, not eternal and unchanging, but dynamic, evolving, expanding into its own future. Measuring the curvature, the cosmic microwave background. There's a picture of the universe that you might have seen before, even if you didn't know what you were looking at. It's an oval map painted in shades of red and blue, with a mottled, slightly irregular pattern of temperature variations across the entire sky. This map shows the cosmic microwave background, or CMB, the oldest light in the universe, and it's one of the most important images in the history of science. Encoded in those tiny temperature fluctuations is information about the geometry of space itself. The cosmic microwave background is radiation left over from the Big Bang. About 380,000 years after the universe began, space had expanded and cooled enough that electrons and protons could combine to form neutral hydrogen atoms. Before this moment, the universe was opaque, a hot, dense plasma where light couldn't travel far without scattering off free electrons. But once atoms formed, light could suddenly travel freely through space. The universe became transparent. The light released at that moment has been traveling through space ever since. Stretched by the expansion of the universe from visible light to microwave wavelengths, it comes to us from all directions, creating a nearly uniform background glow with a temperature of about 2.7 degrees above absolute zero. This is the CMB, and it's the oldest thing we can observe, a snapshot of the universe when it was just a tiny fraction of its current age. But the CMB isn't perfectly uniform. If you measure its temperature carefully in different directions, you find tiny variations, fluctuations of only about 1 part in 100,000. These fluctuations represent regions that were slightly denser or slightly less dense in the early universe. The denser regions would eventually collapse under their own gravity to form galaxies and clusters of galaxies. The CMB shows us the seeds of all cosmic structure. Here's where geometry comes in. The size and pattern of these temperature fluctuations depend on the curvature of space. Think about it this way. Sound waves in the hot plasma of the early universe created regions of compression and rarefaction, peaks and troughs of density. These waves had characteristic sizes based on how far sound could travel in the 380,000 years before atoms formed. When we look at the CMB today, we're seeing the imprint of these waves. But if space is curved, the apparent size of these features changes. In a positively curved universe, light rays converge, making distant objects look bigger than they would in flat space, like looking through a magnifying lens. In a negatively curved universe, light rays diverge, making things look smaller. By measuring the actual angular size of the features in the CMB and comparing it to what we expect based on physics, we can determine the curvature of space. Let yourself sit with this idea for a moment. The geometry of the entire universe can be measured by looking at temperature differences of a few millionths of a degree in ancient radiation. It's an astonishing achievement of observational cosmology, and the first detailed measurements of the CMB came from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, which operated from 2001 to 2010. WMAP measured the temperature fluctuations across the entire sky with unprecedented precision. The results strongly suggested that space was very close to flat, with curvature close to zero. But the most precise measurements came from the European Space Agency's Planck satellite, which observed the CMB from 2009 to 2013. The final results, released in 2018, represent the culmination of decades of effort to map the early universe with exquisite accuracy. Planck measured something called the curvature parameter, which is essentially a number that tells you how much space deviates from being perfectly flat. If this parameter is zero, space is exactly flat. If it's positive, space has positive curvature and is finite like a sphere. If it's negative, space has negative curvature and is infinite. The Planck results showed the curvature parameter to be 0.0007 plus or minus 0.0019. Take a moment to appreciate what this means. The uncertainty range includes 0. Space could be exactly flat, or it could be very slightly positively or negatively curved, but any curvature is so small that we can't measure it with current technology. To within our measurement precision, the universe appears to be flat. This finding is remarkable for several reasons. First, it confirms the prediction of cosmic inflation theory that the universe should be extremely flat. Inflation stretched space so much in the early moments that any initial curvature was smoothed out, like inflating a balloon until its surface looks flat over any reasonable area. Second, a flat universe means we can't use curvature alone to determine whether space is finite or infinite. If space had positive curvature, we'd know it was finite. If it had negative curvature, we'd know it was infinite. But flat space could be either, depending on its topology. We'll have to look for other clues. Third, the near-perfect flatness tells us that the total density of the universe is extraordinarily close to the critical density when you add up ordinary matter, dark matter, and dark energy. The sum equals, to high precision, exactly what's needed for flat space. This is sometimes called the cosmic coincidence problem. Why should these very different components happen to add up to exactly the critical density? Breathe. Let yourself feel the weight of these discoveries. Satellites orbiting Earth have measured the geometry of space by analyzing light from the edge of the observable universe. They've told us that space, on the largest scales, follows Euclidean geometry to within a fraction of a percent. The universe is, in a very real sense, flat. But what do these measurements actually look like? Imagine a graph showing the power spectrum of the CMB, a plot of how much temperature variation exists at different angular scales. This graph has a series of peaks and valleys, acoustic peaks representing the sound waves in the early universe. The position, height, and spacing of these peaks encode enormous amounts of information about the universe's composition and geometry. The first peak, the most prominent one, tells us about the curvature directly. In a flat universe, this peak appears at an angular scale of about 1 degree on the sky. Planck measured it at almost exactly the predicted position for a flat universe. The match between theory and observation is stunning, one of the great triumphs of modern cosmology. The subsequent peaks tell us about the density of ordinary matter versus dark matter, about the properties of dark energy, about subtle features of the early universe's evolution. The CMB isn't just a pretty picture, it's a detailed blueprint of cosmic structure, a Rosetta Stone for decoding the universe's fundamental properties. What makes these measurements even more impressive is the agreement between different methods. When astronomers measure the large-scale distribution of galaxies, when they observe the brightness of distant supernovae, when they study the abundance of light elements formed in the Big Bang, they all point to the same conclusion. The universe is flat to very high precision, with a composition of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Rest now in this knowledge. The seemingly abstract question of whether space is curved has been answered by careful observation. The universe is flat, or so close to flat that the difference is unmeasurable with current technology. This is one of the most precisely determined facts in all of cosmology. The journey to this understanding took decades and required increasingly sophisticated instruments. The Cosmic Background Explorer satellite, or COBE, launched in 1989, first revealed the tiny temperature variations in the CMB. Before COBE, scientists knew the CMB existed and had measured its average temperature, but they didn't know if it had any structure. The discovery of these fluctuations, announced in 1992, confirmed that the early universe wasn't perfectly smooth. There were seeds of structure, regions that would eventually collapse under gravity to form galaxies. But COBE's resolution was limited. The temperature variations it saw were smeared out over large patches of sky. Scientists needed higher resolution to see the detailed pattern, to measure the sizes of the hot and cold spots precisely. That's where WMAP came in. The Wilkinson Microwave Anisotropy Probe, operating from 2001 to 2010, mapped the CMB with much finer detail. It revealed the acoustic peaks clearly for the first time, showing the characteristic pattern of compression waves in the early universe. WMAP's measurements revolutionized cosmology. They pinned down the age of the universe, the density of matter and dark energy, the timing of the first stars, and crucially, the geometry of space. The universe appeared to be flat to within a few percent, but scientists wanted even better precision. They wanted to know if there was any curvature at all, even at the sub-percent level. Planck, the European Space Agency's mission, pushed the measurements to new extremes, operating at the second Lagrange point, a stable location about 1,000,000 miles from Earth, where the gravitational pulls of Earth and Sun balance. Planck observed the CMB for over 4 years with unprecedented sensitivity. It could detect temperature differences of a few millionths of a degree. It mapped not just the temperature, but also the polarization of the CMB, the orientation of the light waves, which carries additional information about the early universe. The Planck team spent years carefully removing foreground contamination from their data. The CMB signal comes from the edge of the observable universe, but between us and that distant surface, there's lots of stuff that emits microwaves. Dust in our galaxy, radio emissions from stars, diffuse gas between galaxies. All of this had to be painstakingly identified and subtracted to reveal the pure CMB signal beneath. When the final Planck results were released in 2018, they represented the most detailed map of the early universe ever created. The curvature measurement was astonishingly precise. The universe is flat to within a fraction of a percent. If space has any curvature at all, it's so slight that it would take measurements across billions of light years to detect it. This precision is remarkable when you consider what's being measured. We're using light from the edge of the observable universe, light that's been traveling for over 13 billion years, to determine the geometric properties of space itself. And we're doing it with enough precision to say that if space curves back on itself, its radius of curvature must be at least hundreds of billions of light years, far larger than anything we can directly observe. But remember, flat doesn't automatically mean infinite. A flat sheet of paper can be rolled into a cylinder, creating a closed surface with no boundary. Similarly, three-dimensional flat space can have a topology that makes it finite. To know whether our flat universe is infinite or finite, we need to look for topological signatures, for patterns in the CMB that would reveal whether space loops back on itself. That's our next mystery to explore, but for now, drift with the wonder of it. We live in a flat universe, balanced right at the critical density, expanding and accelerating, its geometry determined with exquisite precision by careful measurements of ancient light. Topology, the hidden twist in space. We've established that the universe is flat, or very nearly so. The curvature of space is so close to zero that our best instruments can't detect any deviation. But here's the fascinating thing. Knowing the curvature doesn't fully tell us the shape of the universe. We need to know the topology, and topology is subtle. Topology is the branch of mathematics that studies properties of spaces that don't change under stretching, bending, or deforming, as long as you don't tear or glue. A coffee mug and a donut are topologically equivalent because you can continuously deform one into the other. The handle of the mug corresponds to the hole in the donut. What matters topologically is how a space is connected to itself, whether it has holes, whether it's closed or open, finite or infinite. For the universe, the key topological question is, does space connect back to itself? In a simply connected flat space, like ordinary Euclidean space, you can travel forever in any direction without coming back to where you started. Space is infinite in extent, but in a multiply connected flat space, traveling far enough in certain directions brings you back to your starting point, even though space is locally flat everywhere. The space is finite, even though it has no curvature. The simplest example of this is a torus, though we need to think about it carefully. Imagine taking a rectangular sheet of flat paper. The paper is clearly flat. Triangles on it have angles that add up to 180 degrees. Now imagine connecting the left edge to the right edge, forming a cylinder. The surface is still flat locally. Now connect the top edge of the cylinder to the bottom edge, forming a torus or donut shape. Here's the key insight. Even though the torus appears to curve when we visualize it embedded in three-dimensional space, the surface itself is intrinsically flat. If you're a two-dimensional being living on this surface, measuring angles and distances, you'd find perfectly flat geometry everywhere. But if you walk far enough in certain directions, you'd return to where you started. The space is finite but has no boundary. The universe could work the same way in 3 dimensions. Space could be flat everywhere you measure, but connected back to itself in a way that makes it finite. This is hard to visualize because it requires space to be folded in a higher dimension that we can't see or access. But the mathematics works perfectly well, and such universes are perfectly consistent with general relativity. There are actually multiple ways to create a finite flat universe. The 3 torus is one example, where all 3 dimensions loop back on themselves. There are also more exotic topologies like the Klein bottle and various other 3-dimensional manifolds with interesting properties. Mathematicians have cataloged 10 distinct types of flat, closed, 3-dimensional spaces called Bieberbach manifolds. Each of these topological possibilities would leave distinctive signatures in observations. The most striking would be if the universe were small enough that we could see multiple images of the same objects, like looking at repeated reflections in a hall of mirrors. If space loops back on itself on a scale smaller than the observable universe, light from distant galaxies could take multiple paths to reach us, creating duplicate images in different directions on the sky. Imagine living in a 3 torus universe with a relatively small fundamental domain, the basic repeating unit. Looking in different directions, you might see the same galaxy at different stages of its evolution because light from different paths would have taken different amounts of time to reach you. You might even see multiple images of our own Milky Way galaxy at various points in the past. The sky would contain a subtle pattern of repetition. Cosmologists have searched for such patterns in the distribution of galaxies and in the cosmic microwave background. One technique, developed in the 1990s, is called the circles in the sky method. If space connects back to itself, then the surface of last scattering where the CMB originated would intersect itself. This would create matching circular patterns in the temperature fluctuations, pairs of circles in different parts of the sky with identical patterns of hot and cold spots. Multiple searches using WMAP and Planck data have looked for these matched circles. They haven't found any convincing evidence. This tells us that if the universe does have a multiply connected topology, the size of the fundamental domain must be larger than the observable universe. We're inside one repeating unit, so we can't see the repetition. But recently, a group of cosmologists called the Compact Collaboration has developed new methods to search for topological signatures. They're using a technique inspired by a 1966 paper by mathematician Mark Cox, who asked, "Can you hear the shape of a drum? If you listen to the sound a drum makes, can you figure out the drum's shape from the frequencies present in the sound?" The cosmic microwave background is like the universe's drum. The temperature fluctuations contain frequencies, patterns at different scales. The Compact Collaboration is analyzing these patterns in new ways, looking for subtle signs of topology that previous methods might have missed. They're taking advantage of modern computational power to search for hints that space folds back on itself in ways that would affect the pattern of fluctuations. As of now, no definitive topological signatures have been found, but the absence of evidence isn't evidence of absence, as they say. The searches are limited by the resolution of our observations and by how large the fundamental domain might be. If space loops back on itself, but only on scales much larger than the observable universe, we simply couldn't detect it. Let yourself drift with this idea. The universe might be infinite, extending forever in all directions, or it might be finite but wrapped back on itself in dimensions we can't perceive. Both possibilities are consistent with everything we observe. The flatness we measure through the CMB could describe either an infinite Euclidean space or a finite space with complex topology. There's something philosophically profound here, even with our most sophisticated observations and our deepest mathematical theories. We may be unable to determine whether we live in a finite or infinite universe. The ultimate question about the cosmos's extent might forever remain just beyond our grasp. Some cosmologists have proposed even more exotic topologies. Jean-Pierre Luminet and colleagues suggested that the universe might have the topology of a Poincaré dodecahedral space, a finite space with the geometry of a slightly positively curved dodecahedron with its faces identified in a specific way. This model was proposed to explain some anomalies in the WMAP data, though subsequent analysis hasn't strongly supported it. The dodecahedral space is beautiful mathematically. It's one of the possible topologies for a positively curved three-dimensional space, and it would make the universe finite but much larger than the observable universe. In such a space, traveling far enough in specific directions would eventually bring you back home, but the journey would be unimaginably long. These topological considerations remind us that the universe can surprise us. The geometry might be simpler than the topology. Space might be flat and boring locally, but globally connected in intricate and beautiful ways. Or it might truly be infinite, extending forever without repetition or boundary, containing everything that could possibly exist given enough space. Breathe deeply, feel the mystery of it. We've measured the universe's curvature to high precision, but its topology remains elusive. We live in a cosmos that might be finite or infinite, and current observations can't definitively distinguish between these possibilities. The shape of reality itself is a question we're still working to answer. As you rest with these ideas, consider how far we've come. Ancient philosophers debated whether space could be infinite or finite based on pure logic. Einstein showed that general relativity could describe a finite universe without boundaries. Modern observations have measured the curvature to exquisite precision, and now we're using the subtle patterns in ancient light to search for signs that space connects back to itself in hidden ways. The search for the universe's topology continues. New observations, new analysis methods, and new theoretical insights might eventually tell us whether we live in something infinite or something vast but ultimately bounded. For now, we hold the question lightly, neither certain nor despairing, simply marveling that we can ask such profound questions about existence itself. If the universe is flat and infinite, mind-bending implications. Let's suppose for a moment that the universe is flat and infinite, extending forever in all directions without boundary or edge. This is consistent with our observations and seems like the simplest interpretation of the data we have. But if the universe is truly infinite in extent, filled everywhere with matter and energy following the same laws of physics we observe locally, something remarkable and perhaps disturbing follows. There must be infinite copies of you. This isn't science fiction or wild speculation. It's a straightforward mathematical consequence of infinity combined with finite possibilities. Let me explain why. In any given region of space, There are a finite number of ways that matter can arrange itself. Think about a volume the size of the observable universe, about 93 billion light years across. Within that volume, there are perhaps 10 to the power of 80 particles. That's an enormous number, but it's finite. Each particle can be in different positions with different velocities, but there are quantum limits to how precisely these can be specified. The total number of distinct configurations, while unimaginably large, is finite. Now, if the universe is infinite in extent, there must be infinitely many such volumes, and if there are infinitely many volumes, each of which can only be configured in finitely many distinct ways, then by the pigeonhole principle, the configurations must repeat. There must be volumes out there separated by unfathomable distances that are identical to our observable universe in every detail. This means there are other planets exactly like Earth, with the same continents, the same cities, the same history, and on those Earths there are people exactly like everyone you know, living lives that are identical to the lives here. There are other versions of you reading these exact words, thinking these exact thoughts. Take a breath. Let yourself sit with the strangeness of this idea. It's not that there might be other planets with life similar to Earth's life. It's that there must be exact copies, perfect duplicates, down to the atomic level, down to the quantum states of particles in your brain. Infinity combined with finite possibilities makes repetition not just possible, but inevitable. In fact, it's worse than that. There aren't just a few copies of you. There are infinitely many, and not just infinitely many exact copies. There are also infinitely many near copies, versions of you where one quantum event went differently, where you made a different choice, where your life unfolded along a slightly different path. Every possible variation that's consistent with the laws of physics exists somewhere in an infinite universe. Think about what this means for identity and uniqueness. In a finite universe, you are unique, one of a kind. In an infinite universe, you are one of infinitely many. Your experiences, your memories, your choices, none of them distinguish you from your duplicates scattered across the infinite expanse. They're having the same experiences, forming the same memories, making the same choices. Somewhere out there, separated by perhaps 10 to the power of 100 meters or more, there's another you. The distance is so vast that you could never reach them, even traveling at the speed of light for the entire future of the universe. They're causally disconnected, forever beyond the horizon of what you can observe or interact with, but they exist if the universe is infinite. Does this diminish you? Does knowing there might be infinite copies of you make your experiences less meaningful, your choices less significant? Some people feel that way. If everything that can happen does happen somewhere, then perhaps nothing really matters. If every possible outcome is realized in some region of infinite space, then what's the significance of any particular outcome? But consider another perspective. Your experiences are still your experiences. The joy you feel, the love you share, the beauty you perceive, these are real and present in your life, regardless of whether they're duplicated elsewhere. The fact that other versions of you might exist in no way diminishes the reality of your own existence. You are still you, here and now, living this particular life in this particular place. In fact, there's something almost comforting about the idea Every choice you didn't make, every path you didn't take, every version of yourself you might have been in an infinite universe, all those possibilities exist somewhere. The life you imagined but never lived, the person you dreamed of becoming, the alternative histories where things went differently, they're all real, just infinitely far away. Let yourself drift now. Imagine those distant duplicates of Earth, so far away that their light will never reach us, that no signal we send could ever arrive there. On one of them, another version of you is falling asleep right now, listening to these same words, feeling the same sense of drowsy wonder. On another, a slightly different version made different choices and lived a different life. On another, history diverged centuries ago, and the world looks nothing like ours. This is the infinite universe, not just vast, not just old, but containing everything that finite laws allow. It's a multiverse in the most literal sense, not through quantum branching or separate bubble universes, but simply through the logical consequence of infinite space. Physicist Max Tegmark calls this a level 1 multiverse, distinguishing it from other types of multiverses based on quantum mechanics or cosmic inflation with different physical constants. The level 1 multiverse is just what you get from infinite space with the same laws everywhere. It's the simplest, most conservative type of multiverse, and yet it has these mind-bending implications for identity and uniqueness. Some cosmologists have calculated the distances involved. If you wanted to find another planet identical to Earth, you'd need to travel roughly 10 to the power of 10 to the power of 29 meters. That number is so large that there aren't enough atoms in the observable universe to write it out in conventional notation. The nearest exact copy of you might be even farther away, depending on how we define exact copy and how many quantum states matter for identity. Of course, all of this assumes the universe is actually infinite. We don't know that for certain. Space might be finite, but so large that it appears flat within the observable universe, like how Earth appears flat on small scales even though it's a sphere, or space might be truly infinite, and all these implications follow. Rest in the uncertainty. We've measured the geometry of space precisely, but the question of infinity remains open. If the universe is infinite, it contains infinite wonders and infinite repetitions. If it's finite, we live in something vast, but ultimately bounded, where you might be truly unique. Either way, the question touches something deep in us. Are we alone in our experiences, or are we one of infinitely many? Is the cosmos comprehensible in its totality, or does it exceed all boundaries and categories? These aren't just scientific questions, they're existential ones, probing the nature of our place in reality. Let the question rest now in your mind. An infinite universe containing infinite copies of everything, or a finite universe where each thing happens once. Both possibilities are awesome in the original sense of that word. They inspire awe. They stretch our minds to their limits. They remind us how much larger and stranger the cosmos is than our everyday experience prepares us for. The quantum connection, many worlds, and the multiverse. There's another way that infinity enters into modern physics, and it comes from an unexpected direction: quantum mechanics, the theory that describes the behavior of particles at the smallest scales. And this quantum infinity raises its own questions about parallel universes, copies of ourselves, and the ultimate nature of reality. Quantum mechanics is strange. When we're not observing a particle, it exists in a superposition of states, simultaneously holding all possible properties it could have. An electron can be in two places at once, spinning in opposite directions simultaneously until we measure it and force it to choose. This isn't just ignorance about where the electron really is, it's a fundamental feature of reality at quantum scales. The electron genuinely doesn't have a definite position until measured. The standard interpretation of quantum mechanics, called the Copenhagen interpretation, says that measurement causes the wave function describing these possibilities to collapse into one definite outcome. Before measurement, many possibilities exist. After measurement, only one is real. But where do the other possibilities go? They simply vanish, never having been fully real in the first place. In 1957, a graduate student named Hugh Everett proposed a radical alternative. Nothing collapses. All the possibilities remain real. When a quantum measurement happens, the universe splits into multiple branches, one for each possible outcome. In one branch, the electron is found here. In another branch, it's found there. Both outcomes happen, just in different universes. This is called the many worlds interpretation, and it suggests that reality is constantly branching into countless parallel universes containing all possible quantum outcomes. Every time a quantum event with multiple possible results occurs, the universe splits, and since quantum events are happening constantly, everywhere, the number of parallel universes grows exponentially with time. Take a moment to breathe. This idea is dizzying. According to many worlds, there isn't just one history of the universe. There are infinitely many, branching endlessly like an infinite tree. Every quantum coin flip creates new worlds. Every particle interaction spawns parallel realities. You exist in countless versions, one in each branch, experiencing different outcomes of quantum randomness. This quantum multiverse is different from the infinite space multiverse we discussed earlier. In the level 1 multiverse of infinite space, the copies of you are far away, but in the same three-dimensional space. In the many worlds quantum multiverse, the other versions of you exist in parallel quantum branches, separate realities that don't interact with ours. But here's where it gets really interesting. If the universe is also infinite in spatial extent, these two types of multiverses overlap. The quantum branches exist within infinite space, and infinite space exists within each quantum branch. Physicist Max Tegmark has argued that, in a certain sense, these are really the same multiverse, just described from different perspectives. The infinite copies of you across space and the parallel quantum versions of you might ultimately be aspects of the same underlying reality. Let yourself rest with this layered complexity. We're asking whether the universe is infinite or finite, but the answer might involve multiple kinds of infinity: infinite space, infinite quantum branches, or both. Reality might be far more vast and complex than even infinity in 3 dimensions suggests. Many physicists find the many worlds interpretation troubling because it seems extravagant. Do we really need to posit infinitely many universes to explain quantum mechanics? Isn't it more economical to accept that wave functions collapse and possibilities simply cease to exist when not chosen? But proponents of many worlds argue that it's actually simpler. The theory doesn't add anything new. It just takes the wave function seriously, and lets it evolve according to the equations without inserting an arbitrary collapse mechanism. The parallel universes emerge naturally from the mathematics, and while creating infinitely many universes might seem profligate, it doesn't require any actual new mechanism or physical process. The wave function was always describing all those possibilities. Many worlds just says they're all real. The many worlds interpretation also connects to the question of cosmic infinity in a subtle way. In an infinite universe, all possible configurations of matter must exist somewhere. In the many worlds interpretation, all possible quantum outcomes must exist somewhere. These two ideas resonate with each other, suggesting that perhaps reality simply contains everything that's logically possible. Physicist David Deutsch has argued that quantum computers provide evidence for many worlds. When a quantum computer performs calculations, it's processing information across multiple quantum states simultaneously. Where is this calculation being performed? Deutsch suggests it's being done in parallel universes, with each branch of the wave function contributing to the final result. The extraordinary power of quantum computation comes from harnessing the reality of these parallel quantum worlds. But many worlds remains controversial. Critics point out that it doesn't make any predictions different from other interpretations of quantum mechanics. All interpretations reproduce the same experimental results, at least in principle. So how can we know which interpretation is correct? Is this even a scientific question, or is it more philosophical? Let these questions wash over you. Don't struggle to decide what's true. The relationship between quantum mechanics and the structure of the universe remains mysterious. We have mathematical frameworks that work beautifully for making predictions, but their metaphysical implications, what they tell us about the ultimate nature of reality, is still debated. Some cosmologists have tried to connect quantum mechanics to the shape of the universe more directly. In quantum cosmology, people attempt to write down a wave function for the entire universe, describing all possible geometries and configurations in a grand superposition. This universal wave function would evolve according to something called the Wheeler-DeWitt equation, a quantum version of Einstein's equations for the geometry of space. In this framework, the universe might exist in a superposition of having different shapes, finite in some branches of the wave function, infinite in others. The measurement problem becomes cosmic. How does the universe choose which geometry to have? Or does it choose at all? Perhaps all possibilities coexist in the universal wave function. These are speculative ideas pushing at the edges of current physics, but they illustrate how deeply the question of infinity has penetrated into our understanding of reality. It's not just about whether space goes on forever. It's about whether quantum possibilities all remain real, whether the universe's wave function describes one reality or infinitely many, whether existence itself is fundamentally singular or plural. As you drift toward sleep, let go of needing to understand all this completely. The connection between quantum mechanics and cosmic geometry is subtle, complex, still being explored. What matters is the sense of wonder. Reality might be far stranger and larger than we ordinarily imagine. The question of infinity appears in multiple guises, from the extent of space to the branching of quantum possibilities, and we're still working to understand how these pieces fit together. Rest now. The universe, whether finite or infinite, whether existing as one reality or branching into countless parallels, contains you. Your experience is real, your consciousness, your awareness of these questions, your sense of wonder at the cosmos. These are among the most remarkable facts about reality. In a universe asking questions about its own nature through the consciousness that has emerged within it, you are part of that cosmic self-reflection. What we still don't know, the limits of observation. Despite all our sophisticated instruments, all our mathematical theories, all our precise measurements of the cosmic microwave background and the distribution of galaxies, we still don't know whether the universe is finite or infinite. We may never know, and understanding why we can't know, why this question might be permanently beyond our grasp, teaches us something profound about the limits of science and observation. The fundamental problem is that we can only observe a finite portion of the universe. Light travels at a finite speed, and the universe has existed for a finite time, roughly 13.8 billion years. This means light from distant regions hasn't had time to reach us yet. There's an observational horizon, a boundary beyond which we cannot see, not because something is blocking our view, but simply because the light hasn't arrived yet. This observable universe has a radius of about 46.6 billion light years. Yes, that's larger than 13.8 billion light years, because space has been expanding while the light traveled toward us, stretching out the distances. Everything we can observe, every galaxy, every wisp of gas, every photon of the cosmic microwave background comes from within this sphere centered on us. But is that all there is? Beyond our observational horizon, does space continue, filled with more galaxies, more structure, perhaps forever? Or does it curve back on itself, or have some topology that makes it finite? We can't see beyond the horizon, so we can't directly observe the answer. Now, you might think, just wait. Eventually, light from more distant regions will reach us, expanding our observable universe. Can't we eventually see everything if we're patient enough? The answer, surprisingly, is no, because the universe isn't just expanding, its expansion is accelerating, driven by dark energy. Distant regions are receding from us faster and faster. There are galaxies beyond a certain distance whose light will never reach us, no matter how long we wait, because space between us and them is stretching faster than light can cross it. This creates what cosmologists call the cosmic event horizon. It's analogous to the event horizon of a black hole, but instead of surrounding a singularity, it surrounds us. Beyond this horizon are regions of space that are causally disconnected from us forever. We cannot observe them. We cannot send signals to them. We cannot interact with them in any way. They're forever beyond our reach. Take a breath. Let yourself feel the poignancy of this. There's a vast portion of reality, possibly infinite, that we can never observe. If the universe is infinite, we'll only ever see an infinitesimal fraction of it. Our entire observable universe, with its hundreds of billions of galaxies, might be a tiny bubble in an infinite expanse. This observational limit means that certain questions might be fundamentally unanswerable. If the universe has a finite but very large topology, larger than our observable universe, we could never detect it. If space is infinite and copies of our observable universe exist but only beyond the cosmic event horizon, we could never verify their existence. The ultimate nature of the cosmos might be hidden from us by the combination of finite light speed, finite cosmic age, and accelerating expansion. But scientists don't give up easily. Even if we can't directly observe the entire universe, maybe we can infer properties about it from what we can observe. This is where the search for topological signatures in the cosmic microwave background becomes crucial. If space loops back on itself on a scale smaller than the observable universe, we should see matching patterns in the CMB, evidence that we're seeing the same region from different directions. The compact collaboration's new methods for searching for topology represent the cutting edge of this effort. They're using sophisticated mathematical techniques to analyze the CMB in ways that might reveal subtle signs of a finite universe. But so far, no clear signals have emerged. Either the universe is infinite, or it's finite but larger than we can currently probe. There's also the possibility of indirect evidence. The detailed pattern of temperature fluctuations in the CMB depends on all sorts of factors. The density of matter and dark matter, the properties of dark energy, the initial conditions from cosmic inflation, and potentially the topology of space. By measuring this pattern with extreme precision and comparing it to theoretical models, we can constrain what the universe might be like beyond our direct observation. Recent results from the Dark Energy Spectroscopic Instrument, or DESI, collaboration have added new complexity to this picture. DESI has mapped millions of galaxies and quasars across cosmic history, measuring how dark energy has affected the universe's expansion over time. Their preliminary results suggest that dark energy might not be constant but might change over time, which would have profound implications for our understanding of space's geometry and evolution. If dark energy is changing, it means the fate of the universe might be different than we thought. The universe might expand in unexpected ways, potentially affecting whether regions beyond our current horizon will eventually become observable. But these results are still preliminary, requiring confirmation and further study. Let yourself drift now with the uncertainty. Science has revealed so much about the universe, its age, its composition, its geometry, its evolution, but fundamental questions remain open. We know the universe is flat, or very nearly so. We know it's expanding and accelerating. We know it's filled with mysterious dark matter and dark energy, but we don't know if it's infinite or finite. We might never know. This isn't a failure of science, it's a recognition of its limits. Science works by making observations and testing theories against those observations. When observations are fundamentally impossible, either now or ever, the question moves beyond the realm of empirical science and into philosophy and mathematics. We can explore what the possibilities are, what each would imply, but we might not be able to determine which possibility is actual. Some physicists find this frustrating. They want definite answers, observable confirmation, closure on fundamental questions. But others find it beautiful. There's something humbling and appropriate about the universe withholding some of its secrets, about reality being larger than what we can observe and measure. The question of cosmic infinity touches on meaning and significance. If we knew the universe was finite, we'd know that everything that exists is, in principle, catalogable and knowable. If we knew it was infinite, we'd know that existence exceeds all boundaries, that there's no limit to what is. Not knowing means we live with both possibilities, with the mystery of existence itself unsolved. As you rest with these ideas, feel how the question has transformed over time. ancient philosophers asked whether space could be infinite based on logic alone. Einstein showed that the shape of space was connected to physics and could be calculated. Modern cosmologists have measured space's geometry precisely and searched for signs of its topology, and yet the ultimate question, finite or infinite, might remain forever beyond proof. This is okay. Mystery isn't the enemy of understanding. It's the edge of understanding, the boundary where what we know meets what we don't. Living with the question, holding it lightly without demanding resolution, is its own kind of wisdom. The universe is vast, ancient, strange, and possibly infinite. We are tiny, recent, part of that strangeness, asking questions about the whole from our small vantage point within it. Living with the question, the human dimension. Here we are, all these words later, and the question remains open. Is the universe infinite or finite? We've traveled through ancient philosophy, Einstein's revolutionary geometry, precise measurements of ancient light, the mathematics of topology, the strange implications of infinity, and the limits of observation, and we still don't have a definitive answer, but maybe that's okay. Maybe the question itself is what matters, not the answer. Maybe living inside this mystery, being conscious beings who can wonder about the extent of existence, is remarkable enough on its own. Think about what it means that you can even ask this question. You're a configuration of matter that has become aware of itself and curious about the structure of reality. Your brain, 3 pounds of tissue powered by the chemical energy of food, can contemplate infinity. You can wonder about the shape of space itself. That's extraordinary. The question of whether the universe is finite or infinite isn't just abstract science. It touches on how we think about meaning, purpose, and our place in the cosmos. If the universe is finite, everything that exists is bounded, contained, part of a whole that is vast but ultimately comprehensible. There's something comforting in that. The universe is big but not too big, complex but not infinitely so. If the universe is infinite, existence exceeds all boundaries. There's no end to space, no limit to possibility. Everything that can happen, given enough space, does happen somewhere. This can feel vertiginous, destabilizing. How can anything matter if everything happens? How can you be unique if infinite copies of you exist? But it can also feel liberating. The cosmos isn't constrained by any boundary. Reality is generous, abundant, inexhaustible. Different people respond differently to these possibilities. Some find infinity overwhelming, even terrifying. The thought that space goes on forever, that existence has no boundary, no frame, no limit, can induce a kind of existential vertigo. It can make Earth feel infinitesimally small, human life insignificant, individual choices meaningless in the face of infinite vastness. Others find infinity exhilarating. The idea that reality is unlimited, that there's always more to discover, more to experience, more to understand, fills them with wonder. An infinite universe is one where curiosity can never be exhausted, where every answer leads to new questions, where the adventure of understanding never ends. Breathe deeply. Notice how you feel about these possibilities. Are you drawn to the bounded elegance of a finite cosmos or the endless expanse of an infinite one? Neither feeling is wrong. They're different ways of relating to the fundamental mystery of existence. There's a philosophical tradition going back at least to Immanuel Kant that recognizes the question of cosmic infinity as one that reason can't definitively settle. Kant argued that the human mind can generate equally compelling arguments for both finitude and infinity, and that trying to resolve the question through pure reason leads to antinomies, contradictions that can't be logically resolved. He thought this showed the limits of reason, the boundaries beyond which our concepts break down. Modern cosmology has added empirical observations to the mix, giving us constraints that Kant didn't have. We know the observable universe is finite. We know its geometry is flat or nearly so. We know it's expanding and accelerating. These facts narrow the possibilities, but they haven't eliminated the fundamental question. Finite or infinite remains open. Perhaps we'll never know. Perhaps the universe holds this secret forever, withholding the answer about its own extent. And perhaps that's fitting. The cosmos has given us consciousness, rationality, curiosity, the ability to ask profound questions about existence. But it hasn't given us omniscience. We're part of reality, not outside observers able to see the whole. We live inside the question. Let yourself relax into this uncertainty. In our everyday lives, we rarely encounter questions that are genuinely unanswerable. Most puzzles can be solved with enough effort, enough information, enough time. But the question of cosmic infinity might be different. It might be a mystery rather than a puzzle, something to contemplate rather than solve. Living with mystery isn't the same as ignorance. Ignorance is not knowing something that could be known. Mystery is encountering something that might be unknowable, at least to us, at least for now. Mystery invites wonder, patience, humility. It reminds us that we're finite beings in a cosmos whose nature might exceed our grasp. There's beauty in this. The universe is larger and stranger than we can fully comprehend. Space might be infinite, extending forever beyond all horizons, or it might be finite but so vast that the difference is imperceptible to us. Either way, we live in something magnificent, something that inspires awe and wonder and countless questions. You are here now in this universe, whatever its ultimate extent. You are part of the cosmos, becoming aware of itself, asking questions about boundaries and infinity, contemplating geometry and topology and the fundamental structure of space. Your ability to wonder about these things is itself one of the universe's most remarkable features. As you drift toward sleep, let the question rest. Finite or infinite, bounded or endless, the universe contains you. It has given rise to stars and galaxies, to planets and life, to consciousness and curiosity. It has made possible this moment where you lie in darkness, thinking about the shape of existence itself. The ancient philosophers wondered about boundaries. Einstein calculated the curvature of space. Modern astronomers measured the geometry of the cosmos with stunning precision. And you tonight have traveled through these ideas, exploring one of the deepest questions we can ask about reality. Rest now, knowing that the question remains open, that the mystery continues, that the universe keeps its secrets even as it reveals so much. You don't need to understand everything. You don't need to have all the answers. The wonder itself is enough. Let yourself feel small in a way that's comforting rather than diminishing. You're a small part of something vast, perhaps infinitely vast. And that's okay. Your experiences are real. Your life matters. Your questions are worth asking. The fact that some of them might be unanswerable doesn't make them any less important. Breathe slowly. Feel yourself relaxing, letting go of the need to know, to understand, to grasp the ultimate nature of things. The universe is what it is, finite or infinite, and you are part of it. That's enough. Conclusion: resting in wonder. So here we are, at the end of this journey through one of cosmology's most profound questions. We've explored ancient paradoxes, revolutionary theories, precise observations, and mind-bending implications. We've asked whether the universe has boundaries, whether space goes on forever, whether you might have infinite copies scattered across infinite expanses. And after all of that, the honest answer is, we don't know. The universe is flat or nearly flat, expanding and accelerating, filled with matter and dark energy in proportions that bring its total density to exactly the critical value. But whether space is infinite or finite remains uncertain. Both possibilities are consistent with our observations. Both are compatible with general relativity and our understanding of cosmic evolution. In a way, this makes the question even more intriguing. We've learned so much about the universe in the past century. We've measured its age to high precision, mapped its large-scale structure, discovered dark matter and dark energy, traced its evolution from the first moments after the Big Bang to the present day. We've answered questions that ancient philosophers could barely formulate. And yet this fundamental question, one of the oldest and deepest, remains open. Maybe that's how it should be. Maybe the universe is entitled to its mysteries. Maybe not everything about reality is meant to be known, at least not by us, not yet. We're finite beings, living finite lives, observing a finite portion of the cosmos. If the universe is infinite, we're necessarily ignorant of most of it. If it's finite but larger than our observational horizons, we still can't see its full extent. Either way, there's something beyond our grasp. But what we have grasped is extraordinary. We've understood that space itself can curve, that geometry is physical, that the shape of the universe is determined by its contents. We've measured that geometry using light from the edge of the observable universe. We've searched for signs that space connects back to itself in hidden ways. We've calculated what infinite space would imply about repetition and uniqueness. The question of cosmic infinity connects to so many other deep questions. If the universe is infinite, does that mean infinite possibilities are realized? Are there infinite copies of you? Does infinity make everything that happens inevitable rather than contingent? Or is the universe finite, making each configuration of matter unique, unrepeatable, special? These aren't just physics questions. They're philosophical, existential, touching on meaning and value and how we understand ourselves. A finite universe feels bounded, comprehensible, home-like. An infinite universe feels boundless, inexhaustible, sublime in the original sense, beautiful but overwhelming. Take a slow breath. Feel yourself settling, releasing, letting go of the need to resolve the question tonight. The universe will still be here tomorrow, whether finite or infinite, whether bounded by complex topology or extending forever, and so will you, part of that cosmos made of its matter, shaped by its laws, conscious of its mysteries. There's a deep peace in accepting uncertainty. Not every question needs an answer. Not every mystery needs solving. Some things we hold lightly, wondering about them without demanding resolution. The shape of the universe can be one of those things. We've done our best to measure it, to understand it, to determine whether it's finite or infinite. And our best so far has brought us to the edge of knowledge without quite crossing over into certainty. That edge is a good place to be. It's where wonder lives, where curiosity remains vital, where the cosmos still has the power to surprise us. If we knew everything, if every question were answered, what would be left? The unknown isn't our enemy, it's what makes continued exploration meaningful. So let yourself rest now in not knowing. Let the question of infinity remain open, a mystery you've contemplated without solving, a wonder you've explored without exhausting. The universe, finite or infinite, is vast enough to contain your curiosity and humble enough to resist your complete understanding. If you've enjoyed this exploration, if these ideas have sparked something in your mind or touched something in your heart, consider subscribing to this channel. There are countless other questions about the cosmos to explore, mysteries about time and consciousness, about the nature of reality and our place within it. Each one is worth sitting with, worth wondering about, worth approaching with patience and humility and awe. But for now, let the shape of the universe be. Let infinity rest as a question rather than an answer. Let yourself drift into sleep, your mind full of curved spaces and distant horizons, of flat geometry extending perhaps forever, of topological twists connecting space back to itself in hidden dimensions. You are here now, in this moment. The universe surrounds you, whatever its ultimate extent. Space curves or doesn't, loops back on itself or continues infinitely, and either way, it's magnificent. You're a part of that magnificence, a configuration of matter that wonders and questions and marvels. Sleep well, knowing that the cosmos is stranger and larger than any of us fully comprehends. The question of its boundaries or lack thereof will be here tomorrow, still open, still inviting wonder. For tonight, it's enough to have asked, to have explored, to have touched the edge of one of reality's deepest mysteries. Let your eyes close, feel your breathing slow. The universe, finite or infinite, ancient and vast, mysterious and beautiful, contains you, and that simple fact, your existence within this cosmic question, is itself worthy of wonder. Rest now. Rest in the mystery. Rest in the not knowing. Rest in the infinite or finite cosmos that has made you possible. The shape of the universe, whatever it is, has room for you and your questions, and that's enough. That's everything. Sleep now and let the cosmos keep its secrets while you dream.